Today we will play with air tracks to study one-dimensional kinematics. We'll also do some modeling and extract information about the acceleration of our air car from the data. We use the air tracks so that we can simulate a frictionless environment. To do that, we are going to pump some air through the track. It's going to be a noisy lab. The feed screw on the length of the track can be raised or lowered to level the track. When you do the side that has 2 feet, make sure you adjust them at the same time so that it's even. Next, you're going to adjust the Sonic Ranger. The Sonic Ranger will create a cone of sound that'll get wider as you get towards the end of the track, so make sure nothing can obstruct it. The Sonic Ranger works by using the speed of sound to determine the position of an object. In this case, the little flag we have on top of our air car. Although it only measures position, you can use position to calculate the velocity and the acceleration of the air car. You should make sure that you have this set up so that you can see where the air car is along the entire length of the track. If we assume that the Sonic Ranger is at the origin, what would a graph of the air car's position versus time look like as it travels down the track? How could we use that graph to determine the velocity of the air car? What would a velocity versus time graph look like? Would it be above or below the 0 line? And what would the acceleration versus time graph look like? Could the acceleration at all be influenced by friction? Next, we're going to tilt our air track by putting some risers under the single leg of our air track. Now, you might want to measure how thick these are. Luckily, we have these electronic calipers so we can measure with precision. So now that we have our track tilted, what do you think a graph of acceleration versus time would look like? And what would the value of the acceleration of our air car be? To think about it, imagine if we had our air track all the way up at 90 degrees. What would the acceleration be? Alternatively, what was the acceleration when it was at 0 degrees? You may think you need a protractor to measure the angle that the track's at. Nah, you can just use geometry. So we're going to use right angle geometry to figure out the angle that our track is at. You may think that you need to use the entire 2-meter distance of the track as one of the sides of the triangle, but we'll just use similar triangles where one of the sides is just the height of the risers that we've already measured. The other side that we know will be the distance between the 2 feet. There's one foot at 50 centimeters and another one at 150 centimeters. We know 2 sides of our triangle. We can figure out the angle. You just have to determine, do you know the opposite side, the adjacent side, or the hypotenuse? And from there, you can use SOHCAHTOA to figure out the angle that your air track is at. So now that we're all experts on how to calculate the angle of our air track, we can think about some other things, like what would the velocity versus time graph of our air car look like? Would it go through 0? What about the position versus time? And what mathematical expressions can we use to define them? So now we're going to do a physical application. We're going to start our air car here and let go of it. Let it travel to this point where we will hit a stopwatch. You can also use your cell phone. And then stop our stopwatch when our air car gets to this point and see if we correctly predicted the amount of time it took to get from here to here.